All right, hi, my name is James Marshall Reber. Today I'll be talking about the geodesic flow and the Hopf argument. So, I don't know, I guess an apology to start with. I kind of aimed really high and really low with this. So I was like, tried to do things from bare bones, but then also maybe skimmed through a lot of really technical details towards the end. So I maybe missed the target audience entirely, but hopefully it's still enjoyable to watch. Yeah, as I was saying, I follow Einsiedler and Ward really closely, so if there are any details that you have questions about that I'm not able to answer, it's probably in that book somewhere. Uh, yeah, that's basically it. So here's the crash course on the hyperbolic plane, the geodesic flow, and here's where it's going to be probably pretty easy for the most part. So recollection or recall, the hyperbolic plane is the upper half plane in the complex numbers. We can define the tangent plane by just taking the product of a point with the complex numbers. That gives you a vector space. And then you take the union over all possible tangent planes, and that gives you something called the tangent bundle. So these are points in the tangent bundle, basically are just points and then vectors based at that point. And part of what we'll be doing is looking at group actions on the hyperbolic plane, and then in particular on the tangent bundle. And we'll be using that in order to define the geodesic flow. But what actually like makes the hyperbolic plane special is the Riemannian metric. So we have to recall a little bit of Riemannian geometry stuff. So path is a continuous piecewise differentiable function from the unit interval to h. Paths have total derivatives defined in this way. So we have phi of t and then phi prime of t, where phi prime is going from the unit interval to the complex numbers. And then this will be useful to define lengths of things. So the hyperbolic Riemannian metric is defined on the tangent space based at a point, and this is just the usual Euclidean uh, inner product, and then you just kind of normalize by the length of the complex part. And then it gives rise to a norm, which is going to be the Euclidean norm divided by y, the complex part of the number that you're based at. And so this is useful for defining lengths of paths. And so given a path from the unit interval to the hyperbolic numbers, we can define its length via this integral on the unit interval of the total derivative, the norm of the total derivative, which is referred to as the speed of the path at time t. And then once you have these lengths of paths, you can define a hyperbolic metric, and this is the infimum over all possible paths connecting 2 points. So not too hard to check that this actually defines an honest metric, but the details are a little bit messy. I mean, if you just Google hyperbolic metric proof, I'm sure there's a UChicago RU paper that proves it. So if you have any questions about that, there you go. And then a question that you might ask yourself when you see this metric is whether this infimum is actually achieved by something. And the answer is yes, it's achieved by a path called the geodesic path. So this is the length minimizing curve connecting 2 points in the hyperbolic plane. Okay, so that's like the crash course on the really basic stuff. And our goal is to study geodesics, in particular geodesic paths with endpoints on the boundary. So these are called geodesic curves. And the question is, what do geodesics look like in the first place? And this is kind of the basis of everything, is it helps to understand this in terms of group actions. So we're going to look at the isometry group acting on the hyperbolic plane. This will be in the obvious way of evaluation at points. And then this is way too complicated to look at, so instead we're going to restrict to a much easier thing to look at, which are the Mobius transformations. And so define SL2R to be all the 2x2 real matrices with determinant 1. You're going to embed SL2R into functions on the hyperbolic plane by taking this matrix ABCD and mapping it to the function which takes a point and sends it to AZ plus B over CZ plus D. You should probably check that this actually sends points in the hyperbolic plane to the hyperbolic plane. I don't think that's too hard though. So you have this embedding. You can check that it actually is, I guess, a homomorphism, but it defined the image of it to be the Mobius transformations. And you can show that the Mobius transformations are isometries. And so you can define an action of SL2R on the hyperbolic plane in this way. And then kind of the idea at this point is to find geodesics through this action because SL2R is much easier to understand than just looking at all isometries. Okay, but looking at the action in this way is kind of difficult. So instead we're going to push it to the projective plane and look at it there. So define the projective plane by taking all non-zero complex numbers and identifying them if they lie on the same line. You can embed the complex numbers into the projective space by just sending a point z to the vector z1. And you can label this embedding something different if you don't want to call it the same thing. And then we have an action of SL2R on this embedding, which is going to match up exactly with our action of SL2R on the hyperbolic plane when we embedded it into the functions. So the nice thing about this action is it's an action of matrices on vectors rather than looking at an action of functions on points. And if you want to see maybe this equivalence, it's given in this like short calculation here. So looking at it this way helps us with properties of the action of Mobius transformations. And I guess the last remark is that since we're looking at things in projective space, the negative of the identity matrix acts trivially, the identity matrix acts trivially. So plus or minus I2 acts trivially on this H hat. And so we can quotient out SL2R by plus or minus the identity since it acts trivially anyways. This gives us PSL2R acting on H. And so this is the action of Mobius transformations. Okay, so where are we going from here? We want to look at properties of this action. So 3 kind of notable properties. This action of PSL2R and H is isometric. So this verifies the fact that Mobius transformations are isometries. And in this proof that I'm not going to do, but is Nine-Siedler and Ward, you also get that PSL2R acting on the tangent bundle is isometric, which this is a little vague because I didn't tell you how PSL2R acts on the tangent bundle, but we'll get to that in a second. This is required kind of in the proof of showing that the action is an isometry. Another notable fact is that the action is transitive, and also in the proof of this, you get that PSL2R acting on the unit tangent bundle is simply transitive. So just in case you don't remember, transitive just says that you can get from one point to another point via some element in the group. And simply transitive says that that's unique. And then the final fact is that the stabilizer is PSO2, so the projective special orthogonal group, where the special orthogonal group are just the rotation matrices, and then you're going to mod out by plus or minus the identity. So 3 kind of tells us that we can identify H as this quotient space of PSL2R mod PSO2, which this is nice because H doesn't necessarily have any algebraic structure built into it, but this kind of gives it some algebraic structure if we view it in this way. So really this isomorphism should be in quotes because what does isomorphism even mean? H doesn't have any algebraic structure, but we're just gonna like give it the algebraic structure through this identification. Yeah, all the proofs are omitted. I was always told to never give a proof in a talk, but I'm gonna probably break that rule since I have to do the Hopf argument. If you're interested in the details, here are the exact lemmas, lemma 9.1 and 9.2, and Nine-Siedler and Ward. And then, yeah, I mentioned this action of PSL2R on the unit tangent bundle, and how do you even define that action? So this action is going to be through something called the derivative action. And the way this works is that we have this map, we take the matrix and we send it to the function by this identification I talked about earlier. This gives you a function g of z is equal to az plus b over cz plus d, going from the hyperbolic plane to the hyperbolic plane. This map is complex differentiable, so we can take a derivative. When we do that, we get this. And so we can define dg, this like total derivative, in this way. So it's going from the tangent bundle to the tangent bundle. It takes a point in the tangent bundle zv, and the image is going to be just the image of z in terms of points, but then you also want a vector based at that point. And so what you'll just do is take this vector v that's already based at that point and just scale it by this g prime. And this gives you the derivative action. So I guess a fun fact at this point, for fixed z, this gives it a linear map. And then notice that the chain rule actually shows you that this derivative action is an honest action, because you need to show for it to be an action this compatibility feature. And that's what the chain rule exactly says, is this compatibility feature. And so maybe scrolling back up, I said earlier one of these properties was that PSL2R acts on the unit tangent bundle simply transitive. So if we can identify H via this like identification PSL2R mod PSO2, then we can identify the unit tangent bundle of H as just PSL2R. So this gives us kind of an algebraic way of viewing the unit tangent bundle. This will be super useful, not only the transitivity, but this identification in terms of studying like orbits of points by just looking at like maps or PSL2R elements from PSL2R acting on points, and that'll give you an orbit. And so informally, I don't think I ever say these words in the talk, but this gives you a way of viewing like the unstable and stable manifolds via matrices. And that's kind of the crux of the whole Hopf argument. But more to come on that later, I guess. So any questions so far about anything that I've said or any doubts? Yeah, so hopefully this should be standard stuff. I think most people see this in a hyperbolic or Riemannian manifold course. I'm not sure. But with all this buildup, we can finally talk about geodesics. How do you get all the geodesics? So the trick is you're going to take a representative geodesic curve, which will be the imaginary line, and somehow this is the easiest thing to study. Just take like the unit tangent vector II, and this gives you a nice representative thing. This will generate a nice geodesic curve. And then what you're going to do is use this action of PSL2R to move this around. And since it's transitive, it connects 2 points, and it's isometric. So if you trust that isometries preserve geodesics, this will take a geodesic to all other possible geodesics. And so if you just study this representative thing, make sure that this is a geodesic, and you push this around using this action of PSL2R, this gives you all possible geodesics. And so even though we didn't go to the full isometry group and look there, just this like nice representative subgroup gives us all possible geodesics. Moreover, when you study this like nice representative geodesic curve, you get that there exists a unique element in PSL2R, which kind of parameterizes every other geodesic, or every other path, actually, not just geodesic. So every other path can be realized as G, some element in PSL2R, of e to the ti. And this is going to be the crux of showing what the geodesic flow is. So we have this nice parameterization of the geodesic curve, the imaginary line, and then we're going to take this and push it around, and this will kind of uniquely parameterize every other geodesic curve in the exact same way. So again, that's like a very big gap of details here, saying a whole bunch of things really. But if for details, look here, lemma 9.3 and proposition 9.5 or 9.4. And also, if you're curious what the other geodesics look like, you're either going to be a semicircle or you'll be a vertical line. So that gives you geodesics. So in this proof, what you see is that geodesics are basically determined by 2 bits of information. A point in the hyperbolic plane and then a velocity vector. So that tells you basically, like if you take a point here and then a velocity vector here, that tells you exactly where. This is like tangent to the semicircle, or yeah, the semicircle, and this gives you the geodesic curve. But not only that, if you don't care about length of the vector, then it's uniquely determined by an element in the unit tangent bundle. So this tells you how to get basically every geodesic from an element in the unit tangent bundle, which is PSL2R. So here's just like that derivative action happening. Again, you take something in G, or G and PSL2R, take this derivative action, uniquely goes to some other element, ZV in the unit tangent bundle. And so we're just going to basically study this representative vector, II, and push it around. And this gives you the geodesic flow. So you have some other geodesic curve, say L naught, you have, or L, this is some other one, and you have your original representative one, L naught, which was the imaginary line. And the geodesic flow for ZV is going to be defined by doing this derivative action on II using this G that kind of defines the path, and that'll parameterize this one here. So here's like the formal definition. The geodesic flow is defined by following the uniquely defined parameterization, which is given by this proposition earlier, of the geodesic L determined by something in the unit tangent bundle ZV for time t. So in red, what I kind of do is go through the details of how the derivative action works. And so again, I apologize, the notation is pretty terrible. There are a whole bunch of G's and they're all kind of not related. I should have really fixed this before we got here, but that's okay. I'll hopefully just differentiate them with words. So we have that the geodesic flow for the representative vector II looks like this. So this parameterizes the flow along the imaginary line. So what we'll do is kind of define this in terms of matrices. And the goal of this is to eventually use kind of this representation via matrices to also push it to SL2R. That'll make sense in like a bit when we get to the Hopf argument. But that's kind of why we're doing this. So we examine the matrix capital A sub t, given in this form here. And so this is an SL2R for fixed t, and we get that it acts in basically the way that we want this to act. So A sub t does what we want it to do. And here I used ft for whatever reason. This should really just be like gt fixed for the first coordinate. And the derivative action of this ft happens to be the exact same thing. Whatever, sorry. So what this is basically saying is that we can realize the geodesic flow here as something by derivative action of PSL2R. So we have that this derivative action of this matrix on II is the same thing as geodesic flow. And here's where it gets even worse. So take another element and your unit tangent bundle ZV. There exists a unique G in PSL2R that connects II to ZV. This G has nothing to do with GT, and this GT kind of has nothing to do with the other GT. So this GT is the geodesic flow for the point ZV. This GT is for the representative vector II. Somehow they're just kind of like the same thing, but yeah, there's a whole bunch of G's and they're all kind of not related. So geodesic flow for this specific point here is going to be the derivative action of the element from PSL2R acting on the geodesic flow for II. The geodesic flow for II is the derivative action of this original matrix on the vector II. And because we have compatibility of the action, we can rewrite this as d of GAT II. And then for reasons later, we rewrite this as AT inverse, little AT inverse, where you just take it to be the inverse of capital AT. This is just to make sure we have an honest action when we go to PSL2R, because we'll be working with right cosets, and then when we do this derivative action, we want to make sure the compatibility feature works. Okay, so sorry, again, a whole bunch of like nonsense. Does anybody have questions? Comments, concerns?
So can you repeat how the DG works? You're trying to, like this series of equations, you're saying that to get the geodesic flow at the point Z with tangent vector V, you're applying a matrix to the geodesic flow at the point I with tangent vector I. And what, like intuitively, what is this matrix? The total derivative?
Total derivative? Yeah, so this is really just a function which is acting on the unit tangent bundle. And maybe it's better to think of it this way, right? So you're going to have your vector, your geodesic path here, maybe II. So it's connecting two things. This is the geodesic flow for time t. And you want to figure out, you have this other geodesic over here. And you want to figure out if you start at this point here, which is connected by some map G. So this is say I, and this is some point Z. And you want to follow the geodesic flow for Z after time t. What you're going to do is follow it over here for time t, and then map that and see where that goes. So that's kind of what's going on here, is you really go back to this representative thing, you follow that for time t, and then you push it over here. That's what this series of equations is trying to show. And so since we have a nice parameterization, and there was this lemma earlier that said that basically everything looks like this parameterization, this tells you kind of how to relate the two. Does that maybe help with that?
I'm fine with that part. I'm just wondering why a derivative matrix shows up.
because we forced it to, really. So why does a derivative matrix show up? We have G connects II and ZV, and then we have, this is the geodesic flow. So you follow the flow after time t from II, and then you take that, whatever point that is, and you take this back to the other geodesic. And then we want to realize this as a derivative of something, and then we want to use the compatibility to just rewrite this in terms of one matrix in the end, or one thing, yeah. One matrix since G is in PSL2R. So it's really just for notational convenience, I guess.
Okay. I'm satisfied. Thank you.
Yeah, that's a good question. And this is, yeah, why is it notationally convenient? Because we'll eventually want to push this to PSL2R, which doesn't make any sense right now, but will when we get to the Hopf argument for ergodicity. Good question, though. Any other questions? Okay. And then, yeah, notation, we just denote this right multiplication by RAT is of G is GAT inverse. So that hopefully builds up all of the language that we need for the Hopf argument in terms of like what geodesic flow is, and then there's going to be a whole bunch of facts that we'll need on quotients. And the reason we're going to go to quotients is because the geodesic flow on the hyperbolic plane is really boring. Like it's totally, like we know exactly what geodesics look like on the hyperbolic plane. So the more interesting thing is we want to take quotients of the hyperbolic plane and get to different spaces and then study geodesic flow in these different spaces. And I guess for the sake of this talk, we're going to restrict it down to special quotients of H. I'm not sure if you go beyond this, if anything works, but we'll want to take H, kind of identify it with PSL2R, and then we'll want to take quotients of that with respect to lattices. And this will give us something that's interesting to study geodesic flow on. And then a natural question is geodesic flow kind of defines a continuum of maps. Are these maps ergodic? And that's where the Hopf argument is going to answer that question. So yeah, we want to study dynamics of the geodesic flow on quotients of H. So we want to quotient H by a discrete subgroup, or sorry, a lattice, which I define because I mean I'm still new to this stuff. So it's a lattice is a discrete subgroup of PSL2R such that the quotient has fundamental domain with finite measure, which kind of implicitly there's a lot of words built in here. So hopefully recall that a discrete subgroup is a subgroup such that its subspace topology is discrete. Or another way to think about it is that every neighborhood, or for every point X in your subgroup, there exists a neighborhood that intersects just that point. The nice thing here is that we have kind of a improvement on discreteness, which is via uniformly discreteness. So something is uniformly discrete if the distance between every 2 points is bounded below uniformly. And since D is living inside of a closed linear group, D discrete implies that D is also uniformly discrete. And this is an easy proof, so I commit the cardinal sin of proving something. Just take 2 points, which are getting arbitrarily close in your subgroup D for contradiction. So with respect to whatever metric we eventually define, the distance between these points goes to 0, but then multiplying by the inverse is continuous, so that says that you have a sequence of points converging to the identity inside of your subgroup, and this is bad because you want your subgroup to be discrete, and that contradicts discreteness. So that was just like an easy fact. When I say finite measure, what do I actually mean here? This measure is induced by the volume form. So this is called the hyperbolic volume form. This is dm is 1 over y squared dx dy d theta. And a fundamental domain, I don't know, it seems like everybody has a different definition for fundamental domain, but in this case, it just means a measurable subset that nicely cuts up our space. So for all g in PSL2R, we have that our fundamental domain intersects this translate of gamma by g in just one place. So with that, we have this nice fact. If gamma is a lattice inside of PSL2R, the hyperbolic measure for dm induces a finite PSL2R invariant measure on this quotient of PSL2R by gamma on the right. And so this is kind of the basis for doing ergodic theory stuff. And this is found in proposition 9.19 in Einsiedler and Ward. And then this last fact that we kind of need to assume, I don't know, is not very intuitive for me at least, is let G be a locally sigma compact metrizable group, M is left Haar measure, then for all B1, B2 Borel subsets inside of G with the product of their measures being bigger than 0, we have these three properties that kind of seem, I don't know, pedantic out of nowhere. You have that the measure of the translates intersected with each other will be bigger than 0 is non-trivial, so there exists something such that when I translate B1, it eventually intersects B2 non-trivially. And same way going on the right. And then there's this nice fact here, which I don't think we use at all. And this is proposition 8.6. So yeah, here's the actual thing. Let gamma be a subgroup or a lattice inside of PSL2R. Then for any fixed t, we have that the geodesic flow RAT is an ergodic transformation on x, which is the quotient with respect to this measure mx. And I'm supposed to specify this is Eberhard Hopf, not the other one. I was told that it's a bad thing to just say Hopf because I guess there's two of them. I don't know. So our plan for proving this is as follows. I mean, the first step is just normalize the measure, so it's a probability measure. The second step is kind of one I'm not going to really talk about, but it's to show that these two groups generate SL2R. And secretly what I'm doing here is this is the unstable manifold, this is the stable manifold, so these generate SL2R. And kind of behind the scenes what's going on with the Hopf argument is we want to show that a function that is invariant with respect to geodesic flow is also going to be invariant with respect to this like unstable and stable manifold business. And so if you're invariant among these, then we want to show that you're invariant on the entire thing. And then once you're invariant on the entire thing, we want to get a contradiction to get ergodicity. So something I'm not really going to talk about, and I don't think they talk about in the book, but
So
that's, oh, go ahead.
is the as someone who's not very well versed in geometry,
Yeah.
is the point of this observation that like it's a nice basis that you can show things for two generators like elements of U plus, which all appear to be almost the same, and elements of U minus, which also appear pretty similar. And then this is just like the most convenient basis.
Yeah.
And maybe there's a geometric reason for that because it's stable and unstable, but even just looking at it algebraically, they seem like the simplest matrices you could write down. So then once you prove it for a basis, you could prove it for the span.
Yeah, that's
and then
maybe like trivializing it a bunch. Yeah.
well,
Really what's
yes.
going on is, yeah, we're choosing these because what's going to happen is that these are like things that are all going to be asymptotic. And so we're going to use uniform continuity to deduce invariance on these things through geodesic flow. And then that will give us SL2R, the whole thing. So yes, yeah, these are convenient things, nice generators that'll work.
Okay. Thanks.
Yeah, hopefully it'll be clear once we go through like the second step. So the second step is to show that if we have a uniformly continuous function going from x to r, and it's invariant under RAT, then it is also invariant under U minus and U plus. And then this will kind of lead us to what we want. So this gives us basically the idea. But the issue is that we need it for general measurable functions, not just uniformly continuous ones. And so to get that to go from uniformly continuous to general measurable, we're going to use Luzen's theorem and the density. And we'll show that FRAT invariant implies that it's almost everywhere SL2R invariant. And this will give us our contradiction as long as F is not constant. And this is where we have to use that like last fact that I talked about. So showing that U plus and U minus generate SL2R is easy. It's LU decomposition. So you can decompose matrices into their lower triangular and upper triangular, which is what's going on here. So the second step is let a function from x to r be uniformly continuous and RAT invariant. And this is kind of where this derivative action business comes back in. So take points x, and y is going to be some translate of x by an element in u minus. And we recall that at is given by this, ratg is given by this. And so when we do rat and y, we get this, by definition, is the same thing as this. Sorry, I'm saying these and then not actually highlighting anything. Same thing as this. And now we just throw in an a to the minus nt, a to the nt here, and that gives us the right action here. That gives us conjugate of u minus s, which will end up being this. And so as we take larger and larger n, this is going to get closer and closer to 0, where we have to define some metric here. And this metric's chosen in an appropriate way. It's given by equation 9.9, page 301. It's the metric between cosets. But using this sort of definition here, you get that the distance between these 2 points is bounded above by this here, which goes to 0 as n tends to infinity. So for large n, these are basically the same thing. And so by RAT invariance, we get that these two things are the same, these two things are the same, and then these two things are approximately the same by uniform continuity, since these two things are approximately the same. So this holds for all n, and as we let n go to infinity, these end up being the same thing. So that gives you that f has to be u minus invariant. And if you just use RAT inverse instead of RAT, this gives you that it's also u plus invariant. And maybe here you can kind of see why the name unstable and stable manifold. This shows that something is asymptotically, like exponentially asymptotically the same thing when you follow its orbit. Okay, so that was step 2. Are there any questions on that? This shows that for uniformly continuous functions which are invariant with respect to geodesic flow, we have invariance among the u minus and u plus groups. Okay. And then the next step is Luzen's theorem. So a quick recollection of Luzen's theorem tells you that continuous functions with compact support are going to be dense here. So in
There's
particular,
one thing I missed in the previous argument.
yeah, what's up?
What is, I guess I'm missing something about x and y. I know that x is part of that LU decomposition of y, but y, that very last line, like f of x is equal to f of Rn at of x.
Mm-hmm.
So is that the part where you're using some kind of invariance?
Yeah, so we're assuming ahead of time that f is invariant
Oh,
with
the
respect
function f is invariant.
Yeah.
So then, and then by uniform. Okay, sure. It all makes sense now. Thanks.
Yeah. No, I was definitely confused writing it up, so good that you asked something. Any other questions? Okay. So Luzen's theorem tells us density. We can find a compact set K with arbitrarily large measure such that on this compact set K, f agrees with a uniformly continuous function phi. And we're going to want to try to do the same trick that we just did up there, but the issue was when we went up here, we use the fact that these orbits are basically going to be in the same set for all n. So that way we can use this equivalence here. And we're not going to have that they will necessarily be in the same set K. So the trick, and this is like the clever part of the argument, is we want to figure out a set K, or we want to figure out a place where they spend roughly half of their time. Or we want to find that almost every point in K spends roughly half of their time asymptotically in K. And then we could extract subsequences, which they're both in K simultaneously, and then we can use this uniform continuity argument. And so this is like a really clever application of Birkhoff's ergodic theorem. Define the set B to be the set of points such that this G star function is going to be bigger than 1/2, where G star measures on average how often this is in K. The claim is that the measure of this set will be bigger than or equal to 1 minus 2 epsilon. And this is just the ergodic theorem. So set G star to be this. By Birkhoff, we have that the integral of this will be the measure of K, which by Luzen's theorem is bigger than or equal to 1 minus epsilon. And so 1 minus epsilon is less than or equal to this integral broken up. And on these broken up parts, the integral here will be the measure of B. Over here will be 1/2 the measure of B complement. And then you just simplify things, algebra. And again, algebra gives you 1 minus 2 epsilon is less than or equal to the measure of B. So arbitrarily many points are going to be inside of this B. And now we can do the same trick, taking x and y, which are inside of B. Then we get that this is the case. And now we know that they spend half of their orbit, or more than half of their orbit in K, so we can find a mutual subsequence so that they're both going to be in K along the subsequence. And then we can invoke the exact same argument with the uniform continuity thing. And that tells us that it will be invariant on this B, which is almost everywhere. Now this is for a fixed epsilon bigger than 0, and I want to get it almost everywhere, so I need to show that it's going to get bigger, like it works fine under unions. So choose an epsilon 1 that's smaller than epsilon. We can find a compact k1 that's an x, such that the measure of k1 is bigger than 1 minus epsilon 1. F restricted to k1 is continuous. And then this last fact doesn't necessarily follow from like Luzen's or anything like that. But I mean, the trick here is if it doesn't contain k, just take k1 union k. All the other two facts are still going to be true. And you get this result then. Then you can define B1 just like you define B. And then notice that B will be contained in B1, and you can repeat this argument for the new context. So you get that it also holds in this bigger set. And so you can keep going like that, and since it holds for epsilon bigger than 0 arbitrary, you get that there exists an x prime. This should be like a capital X prime, with the measure of this x prime being equal to 1, and you have this u minus invariance for all x and x prime. And then again, just like before, if you want to get it for u plus, do the exact same argument, but anytime I wrote an RAT, write an RAT minus 1 instead. That'll give you u plus invariance. Notice that this is for specifically the element. So I guess I was saying u minus u plus. This is specifically for the element u minus s and u plus s. So we don't have it for the entire thing yet. But to get it for the entire thing, along the way, we'll get it for products of these elements as well. So that'll give us SL2R invariance. So I guess any questions on the clever application of Birkhoff and I guess the extension?
Yeah, can you go back to the G star function, which I think is where you first started using Birkhoff? I'm trying to remember. There was something here that I didn't understand. So why, first off, what is K and why does it have a large measure? Because you're using that its measure is at least 1 minus epsilon.
Yeah, this is from Luzen's theorem. So we're finding a compact set K with measure bigger than 1 minus epsilon, so that on this compact set K, f is going to be the same thing as or it'll be a uniformly continuous function on this compact set.
Okay.
It agrees with the uniformly continuous function.
That makes sense. And then if you scroll down a bit, so why is the integral of G star equal to mx? Oh, I guess you're just interchanging. Never mind. That's just the standard thing. Okay, yeah, I think I just missed that one detail, and then the rest of it seems reasonable. Maybe a little bit, yeah.
Yeah, it's tricky, but like not super hard if you look at the individual steps.
I agree. Thank you.
Okay. And so we've got it for at least this one element u minus s and u plus s. We have sets of full measure such that on these sets of full measure, f will be invariant with respect to this individual element. And now we want to just create another set of full measure such that it will be invariant with respect to their product. So with respect to g is equal to u minus s, u plus t, s and t are just two numbers. And the way you do that is basically just intersect them in a nice way. So if you take x1 is equal to this intersection, then for x and x1, we have that it'll be invariant with respect to u plus t. And now if we take x1, intersect r inverse of u plus s inverse x1, then for y is equal to this, we get that this holds as well. So it'll be f, or it'll be g invariant in that set. And that set has full measure. And so you just keep going like this, and for if you want to take more and more products, you just keep doing like the same kind of trick, and this will give you SL2R invariance since u minus and u plus generate the set. So we can show that we can find sets of full measures such that products with their elements agree, or products with their elements are invariant. And it's almost everywhere, yeah.
I feel like this would work if we had countably many S and T, but S and T are real numbers, right?
S and T are real numbers, yeah. Yeah, I think I had a question about this too. Let's see.
I mean, it's probably something to do with the fact that
Yeah,
the matrices are continuous as a function of S or T. So
yeah, I
maybe
was
if
gonna
you
say just like use density and, or not density, but yeah. What were you gonna say? Sorry, I cut you off.
I'm tempted to say that as well, but I'm just a bit worried because the functions we're still working with measurable sets and not open sets.
Yeah, and Einstein and Ward don't like address this issue either. So I was tempted to just believe it. So you have it holds for products of elements, and so therefore we can find one for each g.
I mean, I guess maybe what was the original thing that we're trying to prove? We were trying to prove that geodesic flow by flowing with a specified time of t or t naught is an ergodic map.
Yeah.
And we said we were going to do this by doing something else with the matrices u plus and u minus. So what were we trying to do with u plus and u minus as the intermediary step?
We're trying to with u plus and u minus, so we get it for each individual element in those things. And then we want to get it for SL2R because that'll give us for basically every element an SL2R. And then that'll come in the next step, why we want this.
So I guess I don't think there's an issue here. So you just want to show if a system's ergodic, that just means it has no invariant functions. So all you need to show to, right, an invariant function just means for given g,
yeah,
f of xg is equal to f of x.
Yeah.
Almost.
Sure,
so once you fix g, you only need finitely many elements of u minus and u plus to generate g. So you're only intersecting finitely many sets of full measure.
Yeah.
So then you might get.
I think I wanted to declare
there are infinitely many g or uncountably many g that may all have different full measure sets, but for fixed g, you only have finitely many that you're dealing
with. I think I wanted to just declare for like you can find a set of full measure where it holds for all of them, but yeah, I think it's fine as long as you fix it.
So we already know that for any individual value of s or t, the set. Wait.
So for any individual
Okay, what is xs minus?
xs minus? Oh, that's just to indicate that this is with respect to u minus s. So we can find one for u minus s with full measure, which will indicate with u minus or xs minus, and then we can find one for full measure for u plus t, which is x plus t.
Full measure sets such that f
It's
is
an
invariant when restricted to those sets.
yes, exactly.
And we can do that for any f, any s, and any t, is what we showed in the previous step.
Yes, so we fix an
Okay.
f, we fix an s, we fix a t, we can do that. And then we just showed we could do it for products, and then elements in SL2 are finitely many.
Yeah.
Products
Okay.
of finitely many things. Yeah. I think I maybe just wanted to say that you could find an entire set where it holds for this entire set. That's not true. You just fix an element.
Sounds good.
Okay. And here's where we want to get the contradiction. So assume that f measurable is not constant, but it is SL2R invariant almost everywhere. Since it's non-constant, we can find these disjoint intervals inside of R for which their pre-images will be neither null or co-null. And then here's where we have to use this earlier fact that there exists a G such that the translate of C2G, or sorry, but C2 intersects C1 will have positive measure. And so this is just because since they're neither null or co-null, the product of their measures will be bigger than 0. And then the next step is at the set DG. So for fixed G, yeah, this is for fixed G. This is where we want to use that fact. Yeah, for fixed G, the amount of elements in PSL2R, which will be an XG, is co-null with respect to this measure. So when we intersect it with this prior set, this gives us a set with positive measure, and so in particular, we can find an element in there. But this is a contradiction, since that tells us that f of gamma h, which is an I1, is the same thing as f of gamma hg inverse because of invariance under G, which is an I2. And that's it. So we've shown that it has to be constant, which implies ergodic. And yeah, arguments not unlike the others. So when I say the others, I mean the other references. But in order to talk about the other references, we'd have to get into stable and unstable manifolds, which secretly we did, but I didn't say the words. So yeah, that's really it. I mean, here's some further references, which gives you some really cool things. I mean, the Hopf argument's a big deal. So Einstein in Wards, chapter 11, gives you a generalization. I think they talk about like nil manifold stuff. I don't know. I didn't read it very closely. The Hopf argument by Kudin gives you a nice weak mixing result. So not only ergodic, but weak mixing. I think you can, no, so I don't think you get the K property, but you get weak mixing. There's this book by Boris Hasselblad that talks about it and gives a history of it. Babelet gives you on the mixing property again. Katak and Hasselblad's Introduction to the Modern Theory of Dynamical Systems gives you an entirely different approach involving the stable and unstable manifolds. And then I also threw in this paper by Wilkinson, which talks a little bit about just like smooth ergodic theory in general. She talks about the Hopf argument. I think she uses the Hopf argument a bunch in her research. So that finishes my talk. Thanks for coming.